Hi, this is Dr. Bay, and here's Bugsy, and today we're going to go over the E2 mechanism. We'll delve into reaction kinetics, Zaitsev's rule, and regioselectivity. So, stay tuned.
Organic chemistry,
Taught by Dr. Bay.
reaction mechanisms,
Reactants to products.
regioselectivity,
Target deconstructing.
molecules, spectroscopy. Soaring through the sky, triumphantly fly, give rise to the complexity of life. Living on a dream across the seven seas, learning about spectroscopy. Organic chemistry.
An elimination reaction is where a beta hydrogen is deprotonated by a base, a double bond forms while a leaving group leaves. Like SN reactions, there are two mechanisms for elimination reactions, which differ by the timing of the bond breaking and bond forming steps. Today, we're going to focus on the E2 reaction, where E stands for elimination and 2 stands for bimolecular, in which there are two species involved in the rate determining step. E2 is a one-step reaction where a strong base deprotonates a beta hydrogen, forms an alkene or pi bond between the alpha and beta carbons, and then the leaving group leaves. So in total, 3 arrows need to be drawn. The first arrow starts from the lone pair of electrons from the base and is drawn to a beta hydrogen. The next arrow goes from the bond between the beta hydrogen and the beta carbon towards the bond in between the beta carbon and alpha carbon. This is the arrow that shows the formation of the double bond. And the third arrow goes from the bond between the alpha carbon and leaving group towards the leaving group to form a new lone pair of electrons onto chloride. So we can plot each of the species on a reaction coordinate diagram, starting with our alkyl halide substrate and base on the left to reach the transition state, followed by the formation of the alkene product. The energy from reactants to the transition state is the activation energy, or E sub A. And the amount of energy between the reactants and products is the Gibbs free energy, delta G, or enthalpy, delta H. So elimination reactions follow Zaitsev's rule, which is a way to determine which is the major product. In general, the major product is the more stable alkene, and there are two trends that help break this down. The first trend is that alkene stability increases as the alkene becomes more substituted. And to determine this, you have to look at how many carbons are bonded to the alkene carbons, not the alkene carbons itself. So I've highlighted in orange each of these carbon atoms. So according to the trend, mono-substituted alkenes are less stable, while tetra-substituted alkenes are most stable. And the second trend is that if you're comparing two di-substituted alkenes, trans or E alkenes are more stable than cis or Z alkenes due to steric interactions. So a trans or E alkene is where the two biggest substituents are pointing in opposite directions, whereas the cis or Z alkenes have their two biggest substituents pointing in the same direction. For specifically E2 reactions, E2 is most favorable when the beta hydrogen and leaving group are oriented anti-coplanar or anti-periplanar. In the molecule on the left, the bromine group and methyl group are anti-periplanar, which is not ideal for E2 to occur. But in the second molecule, bromine and the beta hydrogen are now anti-periplanar, which is a good orientation for E2 to occur. In the mechanism below, the base, OH-, deprotonates the beta H, a new pi bond is formed, and the bromine leaves to form the products. E2 reactions are also considered to be regioselective, which is the preference of one direction of chemical bond making or breaking over other possible directions. If the E2 reaction contains a strong base, then the major product is the more stable, aka more substituted alkene, which is called the Zaitsev product. Examples of strong bases are listed here. However, if the E2 reaction contains a strong, sterically hindered or bulky base, then the major product is the less stable, less substituted alkene, which is called the Hofmann product. Examples of strong, bulky bases are LDA, or lithium diisopropylamine, and KOTBU, or potassium tert butoxide. Now let's go over a few examples of E2 reactions. We have to determine if the base is a strong base or if it is a strong bulky base, which will help decide which beta hydrogen to eliminate from the reactant. In the first example, the base is NaOH, which is a strong base. This tells us that the reaction will prefer the formation of the more stable, more substituted alkene, which is called the Zaitsev product. However, in the second example, since LDA is a strong bulky base, this reaction will prefer to form the less stable, less substituted alkene, which is the Hofmann product. So in summary, the E2 mechanism is a one-step mechanism in which a strong base deprotonates a beta hydrogen, forms a new pi bond in between the alpha and beta carbons, and the leaving group leaves to form the new alkene product. If a strong base is used, then the Zaitsev product is preferred. But if a strong bulky base is used, then the Hofmann product is preferred. Overall, E2 prefers tertiary alkyl halides, a strong base, and a polar aprotic solvent, and the beta hydrogen being deprotonated and the leaving group must be oriented to be anti-periplanar to one another.
Organic.